Good afternoon, everyone. My name is Rajani, and I'm from Division A. The title of the paper I'll be discussing today is Matrix Multiplication with SQL Queries for Graph Analytics. This is publicized by the IEEE in 2020. So as an introduction, what we're dealing with is big data. So big data is categorized by volume, variety, and velocity of data. And the analysis of big data is gaining interest in data warehousing research. So graph analytics remain one of the most intensive tasks in big data analytics. Many research progress on efficient analytical algorithms work outside a DBMS on flat files, which are then exported from a DBMS. However, R and Python are slow to analyze large data sets, especially when data does not fit in the RAM. Additionally, exporting datasets from a DBMS is very slow and redundant. And also, R and Python cannot compete with a DBMS in speed, parallel speedup, and robustness when data size exceeds RAM. So we have some basic definitions for this study. So we take G as the graph where V is the vertices and E are the edges, and N is equal to the number of vertices. The adjacency matrix of G is a N into N matrix such that the cells I and J hold 1 when there is an edge going from vertex I to J and 0 otherwise. So in the database, the graph G is stored in a table E, which has a list of edges, which this is the adjacency list representation. So E will be defined as E, I, J, V, and the primary keys are I and J, representing the source and destination vertices, and V represents the numeric value, like the cost to go from each edge. So in this work, we solve graph analytics via matrix multiplication with E. So this is a proposed system, as you can see in the diagram. So the main idea is to compute matrix multiplication inside a parallel DBMS if there is a matrix product involving a large matrix. This idea is to provide a valuable guideline to split computations between R and a DBMS. It will also help us decide where to optimize the algorithm. So this, in the diagram, we can see that there are many partitions, n partitions, where the DBMS is split into, and it's additionally outsourced to R or Python, which analyzes the data. So the methodology we will follow. So the DBMS is a parallel system with n nodes under a shared nothing architecture. The data analysis system runs on a separate server or one of the n nodes under the assumption that any computation involving a large matrix is always evaluated inside the DBMS using queries. Numerically intense matrix numerical methods are solved in R or Python, but in the result matrix. Optimized SQL queries that are used to perform matrix multiplication are sent to the DBMS, and the result matrix is stored in the DBMS. Then, another query fetches a subset of the result matrix from the DBMS to R or Python, leaving it in the RAM. The program at the client computer connects the DBMS and it maintains a reference to each matrix in the DBMS. Then the program has the ability to evaluate matrix multiplication with its syntax. In general, the large dataset is stored with the native storage mechanism of the parallel DBMS, and small matrices which can fit into the RAM are transferred to R for further processing and analysis. So the first type of matrix multiplication is matrix vector multiplication. So these problems are like the single source reachability, and it can be solved by multiplying a sparse vector S repeatedly by E. So this is the formula which we have for this particular question. And the S0 is the vector such that S0 of I is equal to 1 only when I is the source vertex and 0 otherwise. So the SQL query for this problem is mentioned below. So to optimize this particular problem, so for the matrix vector multiplication, we can replicate the vector S on each working node in the DBMS system, since the size of S is ON, which is small. But we need to partition the table E across the entire DBMS system. Since S is copied to each node, no message passing is required when performing the query. But if we need to iterate the query, the vector S is summarized and repeated across the DBMS system after each join. So the second type of question we have is the matrix multiplication. And this can also be used to solve many different type of graph problems. And this can be expressed as a join and aggregation query, which is given on this particular slide. And we can also use the operators sum, min, or different aggregate functions depending on the type of graph that we are supposed to solve. So this is flexible. So optimization for this matrix multiplication. So for this, we need to do an identical partition. Implementing an identical partition allows joins to occur locally on each node, thereby helping to reduce data movement across worker nodes during query processing. We partition table E and R by the join key. In the query we presented, the edges having the same destination vertex in table E are partitioned in the same node with the corresponding vertices in R, since the join condition is E.j is equal to R.I, and this was given in the SQL query given on the last slide. So therefore, no data movement is required to perform the query. So as a conclusion, so in general, we present a system that combines popular data analysis languages R and Python with our DBMS. So here we're using the most popular data analysis languages along with the DBMS, so it's more efficient. So while the small data that can fit in the RAM are processed in Python or R, the large scale and the macro matrix multiplication is evaluated by queries optimized for the particular underlying DBMS architecture. And additionally, columnar DBMS enables fast multiplication of sparse matrix with no RAM limitation, which the RAM limitation is present in R or Python. So this does not occur in the DBMS. And we can also split computations between R or Python and the DBML SQL queries without messing the analysis system with query plans. So the future scope and how we can further improve this project. So for future work, we can combine the C++ with Python. The matrix multiplication can be processed in the C++ language in a distributed system, and the further and more complicated analysis can be performed in Python. So this method can further optimize the speed and improve the efficiency of our system and can be implemented anytime in the future. And this is about the publications. This is the bibliography, which are the references the author has mentioned in the study. And yeah, that's it. Thank you.